Today, um, video number 6, we're going to talk about the atom, how it's constructed, its parts, and then how to quantify it. What do we know about the structure of the atom? It's taken decades, centuries to tease out that information. For the longest time, atoms were considered just jelly-filled bags. Actually, for the longest time, we didn't even know about atoms. And that's going to be part of the discussion today. Then, how can we use this information to help us understand how atoms interact with one another? We're talking about chemistry here. And also, how can we quantify something that we can't see? All right. First, the major breakthrough was made in the beginning of the 19th century by John Dalton with his proposed atomic theory. Now, this didn't come full blown out of his head. These ideas go as far back as the ancient Greeks, and some of their ideas hinted of an elementary particle of which all matter is composed. What Dalton said, though, was that rather than the entire universe being made of a single type of atom, which got the Greeks in a huge amount of trouble, they went through uh, mental and philosophical gyrations to try to get around that assumption. What Dalton said was that yes, every element that we know of is made of an elementary particle, that is, an atom. And the atom means right? TOM, that's from the Greek tomos, which means to cut or to divide, and A preceding it means not. So it's not cut. In other words, the atom was a concept in which we believed at the time could not be subdivided. But what Dalton said was not just that everything was made of these atoms, but that the atoms of every given element were identical, but they were different from the atoms of other elements. That solved a huge problem that the ancient Greeks ran into. And he also said that in this theory, that chemical compounds are just formed from uh, combinations of these different atoms. And that any given compound always has the same relative numbers and types, that is, elements, of the atoms. And that when compounds or elements interact with one another, when we get reactions, they're just sort of swapping partners. They just trade places with one another. They're just bound together differently. And the atoms themselves are never changed in a chemical reaction. Now, there are several laws that had been developed over the 18th century, particularly, and some in the 17th century, that this theory was combining and making sense of. Remember, a law just says this is what happens, and a theory says this is why it happens. So Dalton was taking all of these laws that had been developed and making sense of them with his theory. At the time, he didn't know about the structure of the atom, but this was a beginning. In the latter part of the 19th century, there was a lot of interest in electricity. And J.J. Thomson was an Englishman working with a device called a cathode ray tube. And I got a picture of it in just a minute, a replica of the original cathode ray tube. He postulated the existence of negatively charged particles coming from inside the atom. And in further experiments, he determined the ratio of the charge of that particle to its mass. He didn't have the technology to determine what the actual mass was, but he was able to determine the ratio of the charge to the mass of an electron. It came to be called. He didn't name it an electron, but eventually that was the name assigned to this elementary particle. Well, the logical conclusion was, since atoms are neutral, we knew that. Since atoms are neutral, then there has to be some positive balance to the negative particles. We had identified the negative particle, but we didn't have a positive particle to go with it. So a theory was developed, a model, that was called the plum pudding model of the atom. And all it said was that we knew we had these negative particles in here. So we just said the rest of the atom was composed of some nebulous positive charge that wasn't associated with a particle. So it's like a plum pudding. If you've ever had plum pudding, the pudding has pieces of plum scattered throughout it. That's what the electrons were. Okay, and that was the prevailing theory for several years. This was a model of the cathode ray tube, and it's just a negative plate, a positive plate, and most of the gas was removed from the tube, and you could play with the particles that were moving. You put electric field around them, you put a magnetic field and see what happened to them, and that's what J.J. Thomson did. So along comes Robert Millikan, who was an American, and one of his research efforts was to characterize this negative particle a little bit better than J.J. Thomson had. So he built this piece of equipment in which oil drops were produced in a vacuum, and then the negative particles would attach to these oil droplets, and they would fall through a hole in the top plate, and then he could adjust the charge differential on these plates, positive and negative, and eventually suspend some of those particles in the middle. And he looked at them using a telescope. And there were various things he could determine about the rate of fall, the strength of his electric field, and he could determine the charge on each droplet. So after thousands of attempts and lots of work from graduate students, what Millikan determined was that the unit charge of an electron was 1.6 times 10 to the minus 19th coulombs. And coulomb was just a unit of measure. At the time, it was, we don't have time to go into that, but it was well understood the size of this charge. This was the elementary charge on an electron. Well, since he knew the charge on the electron, he was able to calculate the mass based upon J.J. Thomson's work, where he had the charge to mass ratio. If you know what the charge is, then you can calculate the mass. And this is the mass that he calculated, and it's very close to what we have determined with more exacting measurements in recent years. It's very, very small mass. Okay. He did some other work on the electron and experimentally confirmed Einstein's photoelectric effect equation. So Einstein got a Nobel Prize for his publications related to the photoelectric effect, and we're going to talk about that. Let's see. I'm not sure if it's in this. No, I think it's in another discussion. And then Millikan did some work that confirmed Einstein's photoelectric effect. So we had the theoretical versus the practical application. Okay. I don't think I have the video in here because it takes too long. That was holdover from a previous slide set. So we're going to move on, and we'll back up just a few years to understand what's coming. There was also a lot of work toward the end of the 19th century with radioactivity. And of course, Marie Curie and her husband did a lot of work with radioactivity, and they paid the price for it because they died of radiation sickness. They didn't know about it at the time that that was the cause, but we do know now that that's what killed them both. But Henry Becquerel, who was French, discovered radioactivity from uranium, and ultimately three main types of radiation were identified. Gamma rays, which is just high energy light. Beta particles, which are high-speed electrons coming from the nucleus. And alpha particles, which are just helium nuclei, which have, we'll learn later, have 2 protons and 2 neutrons. Well, the reason that I introduced this is because those alpha particles are going to be used in a subsequent experiment coming up. And that was performed by Ernest Rutherford in England in 1911. Well, he and his graduate students and research assistants did the experiment. And essentially what they found, and this is often referred to as the gold foil experiment. What Rutherford was proposing was this plum pudding model of the atom was completely wrong. He said that a better explanation for the structure of the atom was having a nucleus here that was very dense and had contained most of the mass of the atom. And then the electrons were out here, right? And since the electrons have very little mass, that's essentially empty space. So he devised an experiment to prove, to differentiate between the plum pudding and his model. And what he determined was that his model was correct and the plum pudding model was not. You can go on the internet and look up the gold foil experiment from Ernest Rutherford and see animations of what happened. We don't have time for it now. But this gold foil experiment proved that his model was correct and the plum pudding model was dead. Remember earlier on, I explained that there are several things you can do when your theory falls apart, right? You can modify it, right, to take into account the differences in results of your experiments. You can restrict its application, right? Or you can throw it out and start over. And that's what happened with the plum pudding model. It was thrown into the trash can, and now we have the nuclear model that better explains outcomes of experiments for the nature of the atom. So what we determined was with this and subsequent experiments was that electrons are found outside the nucleus, and they are negatively charged particles. Protons are much, much heavier, about 1,800 times heavier than the electrons, and they're contained in the nucleus. They have the positive charge equal in number so that they balance the electrons. And then there was another particle that a research associate of Rutherford, James Chadwick, who discovered the neutron. See, Rutherford realized that the mass of the atom was not fully accounted for by just protons. So he gave this task to his research associate, former graduate student and then research associate, James Chadwick. And Chadwick along with other graduate students, found the neutron, and that covered all the elementary particles from which atoms are constructed. Okay. So this is just a relative representation of the atom where you have the nucleus is very small but very dense, and the overall size of the atom is where the electrons occupy that space. Now, since we identify each of the elements based upon the number of protons. So hydrogen has one proton. No other element has only one proton. Helium has two protons. The number of protons determines the element. And then you have the number of electrons to balance the proton charges. There was also discovered, once we knew about the neutron, that we could have elements, atoms of elements with different numbers of neutrons. So we can have a hydrogen atom with one proton, right, and one electron. We could also have one with one proton and one neutron and one electron. We could also have a hydrogen with one proton and two neutrons, right, and one electron. The only difference among those atoms is the number of neutrons, and we call those isotopes. Isotopes are important for for several reasons, but for chemistry, for determining the mass of a collection of these atoms, because some of them are going to weigh more than the others. Right, so we have to work our way around that, and that's coming up. Here's another example where sodium has 11 protons. Both of them have 11 protons because that's sodium, and 12 neutrons in one isotope and 13 neutrons in another. All right, when we write the chemical symbol, and hopefully you've memorized several of these, when we write the chemical symbol, and I'm going to use an X for the symbol because we don't have any elements with just X. There are 4 positions around that symbol that are reserved for specific information. This location is the number of protons, right? This is the atomic number. This is the mass number, and it's equal to the number of protons plus the number of neutrons. This is for the charge, and this is for the number of atoms. Right? If you have a compound, that tells you how many atoms are in that formula unit. Okay, you can always find out how many neutrons are in this expression by just subtracting A minus Z, and that will give you the number of neutrons. So if we have a certain isotope that contains 23 protons and 28 neutrons, what's the mass number? Well, the mass number has to be 51, right? 23 plus 28. What's the element? Well, if we know 23 protons, we can look in the periodic table and find that 23 protons identifies vanadium. All right. Now let's say a little bit about the chemical bond. We're going to go into more detail about chemical bonding later, but this just introduces the concept. Chemical bonds can either be transferring electrons from one atom to another, or we can share them. If electrons are shared between atoms to form a bond, we call that a covalent bond. And the collection of atoms that form in this covalent arrangement are called molecules. They behave as single units. The ionic bond is a little bit different. When electrons are transferred from one atom to the next, that produces an unbalance in each of the atoms. So let's use, for example, if we have a sodium atom, right? Let's go back, right? With 11 protons, and we're not going to specify isotopes at this point. Right? We're going to assume all isotopes behave chemically the same, so we don't have to worry about that. But there are 11 protons and there are 11 electrons. Chlorine, on the other hand, has 17 protons and 17 electrons. Okay? And at this point, they're both neutral. But from our study of the periodic table, you know that we've got metals on one side, nonmetals on the other. Metals like to give up electrons when they interact with nonmetals, and nonmetals are all too happy to accept them. So what happens is one electron is transferred over here, right? So now we only have 10 electrons here, but we have 18 electrons over there. What does that do to the charge? Well, you can't charge an atom by changing the protons. If you change the protons, you change the element, right? And that's a nuclear problem. If you want to change the charge on an atom, you have to do it with electrons, either add or subtract electrons. So we subtracted one electron. That means now we are excess one proton, positive charge. On this side, we're excess one electron. That's a negative charge. Okay. With this complete transfer of electrons, you get a positive ion over here that we call the cation, and a negative ion over here we call the anion. And what happens is, now that you've got these separation, these different charges, positives always attract negatives. That hasn't changed. And you get this electrostatic attraction. Okay. And that's the formation of the bond. But they're different than molecules. Molecules form these units that behave separately like that. Ionic compounds still have all their ions in the crystal structure, so that you have sodium, chlorine, sodium, chlorine, chlorine, sodium. You have all these ions in this structure, and you really don't have a single unit of one sodium and one chlorine bound together. It's an ionic matrix. Okay, so I'm going to skip this one and this is just describing the atom. We went deeper and deeper. We came to a better understanding of the atom with Niels Bohr's model, and then we came to Erwin Schrodinger's wave equations, and we get to the quantum mechanical atom. Right, but we don't have time to discuss these in detail. So now we know these subatomic particles make up every atom. The number of protons carries the positive charge, but that also determines the identity of the element. Okay, this just is relative masses. And you see that the neutron is just slightly heavier than the proton. We mentioned this. Atoms are neutral because the protons and electrons balance. If you change the number of electrons, either subtract or add, then you create respectively a cation or an anion. And we talked about the atomic number of protons, the mass number, which is the protons plus the neutrons, and we talked about isotopes. This slide set has too many slides in it. So let's skip these because we don't need them. Now, let's talk about how we quantify these elements. It goes back to the question, how do you quantify something that you can't see? Well, what we had to do was through various experimental methods, we had to determine had to actually assign a mass to a standard atom. And then everything else is built from that. And that standard atom is carbon 12. Carbon, 6 protons, 6 neutrons is our standard. And it will always be assigned 12 atomic mass units. Now, the other isotopes of carbon are relatively smaller amounts. Like this carbon has an extra neutron, but it's only 1%. These values, these atomic mass units, are assigned relative to the carbon 12 isotope, and everything else is built around that concept. Well, what you see in the periodic table is the atomic mass is a weighted average of the isotopes that are available in nature. And if this one contributes 98.89%, as 0.9889 times 12, and then 1.11% is 13.0034 atomic mass units, then you see that this weighted average gives you a different value. And this is kind of like doing a grade point average, right? Some classes are worth more than others. And we can determine the relative abundance of each of the isotopes using a mass spectrometer, and then assign the weighted average to this naturally occurring element based upon its isotopic distribution. All right, so I'm going to have to skip over that, and I'm running out of time. So this concept, how do we quantify these elements? Well, atomic mass unit is not something that we have in our lab. We can't weigh atoms in atomic mass units. We just don't have the balance for it. But we can weigh in grams. So what we did was we devised this unit called the mole. It's a number of things, and it's based upon the carbon 12 isotope as our standard. And if we have 12 grams of that isotope, then we have exactly 1 mole of atoms. 6.022 times 10 to the 23rd atoms comprises a mole. And if we have that many atoms of carbon 12, we will also be able to measure 12 grams. And from there, we assign those masses to all the other elements. So when you look at the periodic table and you see, all right, you see this number here that's the number of protons, and you see another number that has a decimal fraction after it. That's the weighted average atomic mass in grams for that element. That's called the molar mass. And if we go to, let's see, I'm going to skip that for now. The mass in grams of 1 mole of a substance is that value. So this is the one for nitrogen, and I usually round it off to 2 decimal places. If we have a compound, then you just take the molar masses of each of the elements. If there are more than one of them, say 2 times what hydrogen is, and 1 plus what oxygen is, add them together. That's the molar mass of that compound. And if we have parentheses, you have to propagate the subscript through the parentheses. So we have 2 nitrogens, we have 6 oxygens, and we have 1 barium. That's the molar mass of barium nitrate. Okay, that's it for this discussion.